Good morning. Is the mic working? Yeah, great, terrific. I want to take you in the realities of implementing AI and trying to actually have impact with it. It's actually, as you all know, more difficult than actually all of us had expected. The potential is huge. We all know that. This is work from the McKinsey Global Institute we did a couple years ago on the potential of analytics. The scale is in trillions. I don't know how to do trillions. So the global economy is 90 trillion. Impact of analytics is 10. AI is a subset of that. About a third is the potential of AI. AI is not the recipe to all problems. At least in this work, it was about a third. And frankly, that's what we tend to find in our actual client work. Two big spheres where the potential is in the commercial area, sales and marketing, and in the manufacturing and supply chain areas. Those are the two big potential areas. Now, it's easy for consultants to put a chart like this together and put trillions on it. It's a lot harder to actually deliver the trillions on the bottom line. And so I want to walk you through two examples, one in the commercial space, one in the manufacturing space. One company you know well. The other one is a leading manufacturer of copper, global manufacturer of copper. And I'm going to use those two success stories to walk you down the complexity of delivering the goods. Kalen, CEO of Air Canada, has made it clear AI is going to have a big role to play at Air Canada. He's launched a fairly substantial transformation effort. Both companies have allowed me to talk about these two cases, as I said. He's gone down a transformation. Most transformations look like this, by the way. There's usually a bit of a strategic alignment phase for a few months, get the top team to decide what they're going to do. They then follow on. We're starting to drive technology in the areas selected. And there's always a big part of capability building around talent, around knowing how to work differently, around the technology stack. And I'll talk about these components. At Air Canada, they took the time to actually take the management team down a journey. That is often forgotten. Right now, we love to jump to the technology right away. That's a mistake, in our opinion, at McKinsey. You should take the 2 or 3 months to actually align the top team. What is AI? What is a data engineer? How is that different than a data scientist? What is a technology stack? What am I going to do about data management? What exactly does that mean? There's got to be some amount of alignment before you start the journey. And so they did that, a learning journey. Then you have to decide where to start. And it's more complicated than just use cases. And I'm going to walk you down this path on the next slide. And then lastly, you've got to have a business case. In the digital world, we love to say, well, it's digital. We don't really need a business case. We'll figure it out. It's agile. It doesn't work like this. Good old business case with investment and return are still the currency to actually get any traction on meaningful investments. Now, this is the map that Air Canada's team created. You'll organize, anybody that's been on an aircraft will recognize airlines' basic organization building blocks. These are domains. They're not use cases. Domains are basically the way the company organizes. It can be by journeys. It can be by function. And what's important is any one of these domains will contain a portfolio of use cases, usually 5, 10, 15, that will deliver the true transformation impact that domain might get. At Air Canada, you got value that they quantify on the y-axis, and complexity and feasibility has to do with how hard will it be to get the data? How hard will the change management effort be? Are we ready in that area to go through something like this? They picked cargo. And in cargo, they selected a set of 10 use cases. The reason why it's important to start with domains and not use cases is the following. If you start with use cases and you prioritize, you will find one in any one of these bubbles. And you will say, we'll do one here, we'll do one there, we'll do one there. But a single use case rarely has transformative power. And if you do that, the executives in charge of any one of these bubbles that use case will be priority number 30. It'll be just an experiment. Nothing that's really quite important to the running of the business. But if you concentrate 10 use cases in cargo, you can have transformative power in cargo. You can truly change the economics and the way cargo operates. And that is true for any single one of these domains. That's why the lens needs to be flipped. We start with domains. We explore domains, get economies of scale in the way we develop AI in these domains, and then move to the next one once that first one has been exploited. So I'll go down the cargo domain with you. We always forget, well, not always forget, but we tend to skip, what's the problem to solve? We haven't developed any code at this point. We're already 2 or 3 months down the journey. What's the problem to solve in cargo? Problem to solve is, on capacity-constrained routes, 20% of the cargo is empty because there's last-minute changes. People who book cargo cancel their cargo. And so how do we solve for that? And then in general, the overall utilization of the cargo space, this is the cargo space in the commercial aircraft that you and I fly in, is underutilized. Why? Sorry, trying to flip through. This is the loading 30 days before in an aircraft. The top graph is passengers. The different lines are different routes. And then the bottom graph is cargo. So cargo is a last-minute business. The bookings get done in the last 5 days prior to the craft going. And there's a lot of variation. This is going up, new bookings, or change in the weight of the booking, going down, cancellations, or change in the weight of that, reduction in the weight of that booking. All of this to say, these are going to change by routes. They're going to change by weather. They're going to change by geography. They're going to change by economic cycles. Lots of variations, and that explains why it's so hard to fill the cargo. Good problem for AI. And so they went after this problem with AI. 2 steps. Fairly classic. There's a first step that we all know about. There's a minimum viable product step. At Air Canada, it's called the AI lab. And this is really where you're in development. You're trying to figure out how to construct this AI model to deliver a prediction on the capacity and a prediction on the no-show that you're going to get. That's standard, but that's not enough. You got to go through another phase once you've proven that this works. That's a scaling phase, productionization of the AI. And frankly, that phase is harder than the first one. This is where you actually put the code at scale, so you don't just prove on 10 routes. You have it run on 1,200 routes. You have it run day in, day out with the data pipelines that are working. They call that, at Air Canada, their factory. 2 different skill sets. The factory is manufacturing-like skill set. The lab is innovation-like skill set. And of course, the rollout and adoption, and I'll talk about that. It's one thing to have it work. It's another one to have it used. What are the skill sets needed? I just thought I'd give you a snapshot. This application so far, just on the utilization of the cargo, has used about 15 FTE. 14 different skill sets around that wheel. 14 different skill sets. This is not just data science world. It's a team sport. A lot of different skills come into play. 40% business skills, actually, and 60% technologists. That mix tends to hold true in all of the work that we do, 50-50 or close to. How does the work split across the phasing of the project? And so you have the same 15 FTEs here, but organized across the business casing phase at the beginning, 12% of the resources consumed there. At the very end, which is the change management phase, 25% of the resources get consumed there. The data science is 15% of the overall resource needs of this. And that's typical of what we find. Less than 20% of the resources is the data science problem. 80% of the resources go to everything else to make this work. Of course, you got to bring all of these people to work in Agile. That's really classic. This is the inside of the room. At Air Canada, nothing special about it. But what is special is bringing folks with the AI technology talent, folks from IT, because there is a need to connect to legacy systems, and folks from the business. I want to shift gear and talk about two technology components of this problem. First is, what is the technology stack we need to productionize this code? And the problem here, to put it simply, is we got all of these data sources at the bottom, 5 major systems that Air Canada needs to connect to, and we got these applications at the top. So the first one, the one that I've been speaking about, is capacity booking. How do we get predictions right so that people who book cargo book enough cargo, push enough cargo, so we maximize the space and the weight that we have? Well, of course, these predictions rely on data that we have in different systems, sometimes our systems, sometimes external systems, like weather. So the first layer is about extracting the data. This is a piece of data engineering, cloud engineering work. We're not developing any model at this stage. We're just surfacing the data to the cloud. This is done through piping that's called APIs and ETLs, and then it eventually makes its way at Air Canada in an Azure-like data lake. Data goes in raw form, partially transformed form, and then a consumable form, consumable for the AI. Then the AI comes in. First generation are typically developed in Python. This is in the lab. But industrial generations are replatformed onto Spark, much more robust and parallelized in terms of application. And then eventually, you got to connect the same type of connectors to your front-end application. That kind of architecture is in every company that's going to do AI at scale. Okay? It's going to be different tools. But the notion of decoupling the legacy system data and being able to expose the data through a cloud layer is a classic architecture solution. And if you don't have that, you don't have AI at scale. The other piece of tooling, and we're finding this increasingly in our work at McKinsey, is to develop code, AI code at scale, you actually need good tooling. This is the architecture of one of the early versions of the model. The circles are data inputs, outputs, so like passenger booking. The squares are compute. The two big squares at the bottom are the two big AI models, one for the capacity and one for the no-show. And then we get to the final prediction. There's a tool behind this called Kedro, in this example, that helps manage the entire code. And it helps figure out where bugs appear when codes get upgraded, get featured up with new features. There's 200 features here that feed the production of this code. It's not a lot. This is normal business as usual code, nothing special about it. But if you don't have underlying tooling to support the development, then you stall. And so increasingly, the name of the game is tooling, less than algorithm. And then we get to the fun part, which is now we got to get this thing to get adopted. There's somewhere between 100 and 150 people that do cargo booking at Air Canada around the world. How do these people do their work day in, day out? And so there's a lot of understanding what the users do in their day-to-day, and this is a solution that's on the left. So they needed to create a whole new front-end interface that feeds right into the workflow of people who do cargo booking. Simple enough. You would have expected that. Most AI solution will end up with the front interface for a user. What you would not have expected is what happened to us on the right. Once we started to book more and more cargo, things were great. And then we found out at some airports, the packing of the pallets weren't being done well. And so what we thought we would be able to optimize, we weren't optimizing because the palletizing wasn't done the way it should be done. And that is a lesson we learn over and over again. As soon as we solve the AI problem, we start to run into problems that have to do with the operating model of the company. And one after the other, you got to be investing time to go and unlock these other bottlenecks before you realize the value. So there's an effort now to figure out where are the places where the palletizing isn't being done well, and go do the standardization of how palletizing needs to be done. You need to measure. And so in this case, a set of control routes and a set of test routes. And then you can see the delta that's been created with this model. It's about 10 points of capacity utilization increase, If you're in the cargo business, you know that that flows all the way down to the bottom line. So these are meaningful impact results. I want to shift gear and go to Freeport-McMoRan. We're going to go into the world of copper. Here again, there's a belief increasingly in resource industries that the AI is going to play a big role, especially around equipment that are bottleneck equipment. If you're in a copper business, I'm going to spend too much time on this, but you dig copper out of the earth. You run it through this first staging in gray area, which is basically grinding. Big boulders, smaller boulders, little fine grains. Go through 3 steps. And then you take these micron-level particulates, and you get them to react with some chemicals, and then the copper floats up at the surface. That's the second part of this process. That's what we're trying to optimize. We're trying to optimize the throughput, how much ore we can run through this, and we're trying to optimize the recovery, how much actual copper we're going to recover from the process. 2 parameters. Why is that an interesting problem? Because depending on the ore characteristics, and here we've shown 7 different ore characteristics at the bottom, the throughput and the recovery can be quite different. Now, this equipment, there's about 300 different set points. And so the operator has 300 different dials that can be set to try to optimize this throughput. The AI basically works like this. Crunch a bunch of data that's been accumulated in different systems, same kind of stack that I've showed you. The model generates a recommendation for the operator. Operator reviews the recommendations for all the different set points of the equipment, and that's done every 3 hours. Now, when you do that, here's the reality on the ground. And I'm going to tie back to some of the points that Gary just made in the previous talk. When you do an effort like this, you have to start with operators, metallurgists, and of course, people who know how to build technology and AI. As soon as you get your first recommendations, you have to review the fundamentals with metallurgists. Do the recommendations make sense when you get it down to first principles in metallurgy? And if they don't, you're dead. It's no longer going forward. They have to make sense. And so the AI cannot just take you anywhere. It has to take you to a place where people believe that it respects metallurgical principles. Then you need to actually work with the operators to say, here's how you're now going to review every 3 hours your set points and make decisions differently. A whole lot of training, and that training needs to go to the supervisors as well. And then eventually you have a system that people believe in and are ready to test. I know you need me to wrap up. I'm wrapping up in 2 slides. I want to give you another example, data. The AI was suggesting, hey, we're operating at a pH of 12. We should be operating at a pH of 10. We'll get more throughput. But the practices were to operate at a pH of 12. They had bad experience at lower pH with some spillage and overreactions. And so then we needed to chase a whole line of things. The sensors were bad. We had to replace the sensors. And we had to create transfer functions to recalibrate the entire data set to the bad sensors. Then we had to basically move in and say, hey, we don't have a whole lot of data in the 10 pH because we used to run at 12 pH. So run new experiments to augment the data set in the range where we thought there were more potential. Retrain the team to say we're now going to run at 10 pH, not 12, when they had been used to say you never go down below 12 because you're going to get trouble. So a whole retraining of the operations as well. This is the chart that Freeport presented in their Q1 results. They're getting 10% incremental metal output from these facilities. Anybody that's worked in mining knows that's very, very hard to achieve. I'm going to close with this slide. A couple of lessons learned, at least for me on this journey. Don't skip the business alignment phase at the beginning. You need more than just, we like AI from the business side. You need the business side to say, we're ready to invest in a business case. Here's the investments. Here's the return we're expecting. Capabilities are crucial. You cannot do AI at scale without having gone through some of the 4 capabilities that I've outlined here. And lastly, don't underestimate adoption and operating model change. A big change management effort. 50% of the efforts tend to go in that last box, and we forget about it. I tell my clients, for every $1 you invest in technology, keep a dollar to invest in a change management effort. Thank you.